All right, so problems in chapter 8. Okay. So this one says a force of minus 5x squared plus 7x in newtons acts on a particle. How much work does the force do on the particle as it moves from x equal to 2 meters to x equal to 5 meters? Okay. So A, you've seen that the work done is this integral dx. So in our case, yeah, that's the force. So 5x cubed by 3 plus 7x squared by 2, and the limits are 2 to 5. Okay. So this is minus 5/3, 5 cubed minus 2 cubed plus 7/2, 5 squared minus 2 squared. All right, so the work done is minus 5/3, and that's 125 minus 8, that's 117, plus 7/2, that's 25 minus 4, 25 minus 4, 21. Okay. And all right, you can get that number, so we won't worry about that. All right, actually I'll do that. So $39, and so 390, 195, and that's 147 plus 73.5. Okay, so that's how much work is done. The work done is negative, so this is bleeding energy from the system. Okay. All right, so part B says, picking a convenient reference point, so there's a typo, but anyway, find the potential energy of this force. Okay, so you saw that, so when there's potential energy associated with this force, that means this is a conservative force. It just means that the force can be written as the derivative of a potential. Okay, so the potential energy and the force are related like so. So you saw that. Okay, and they're asking you to find this function, d function u. Okay, so what we'll do is we'll just take an indefinite integral. Okay. This is just, of course, integration and derivatives are inverses of each other, so this is just minus ux, and we're taking the indefinite integral of this function, minus 5x squared so this is minus 5 over 3 x cubed plus 7 over 2 x squared plus c equal to negative ux. All right, so ux, the potential energy function, is 5 over 3 x cubed minus 7 over 2 x squared, and minus c, well, we'll just call it a new constant, so we'll call this c prime and c. So here is the potential energy function. Okay. Now there's a typo in this problem. So picking a convenient reference point of the potential energy to be zero at x equal to infinity, find the potential energy of this force. Okay, so here's the potential energy, and if you plot that, so for c equal to 0, the plot of this function is given. See, this is 1.67, this is 3.5. Okay. So there's the function. For negative x, this dominates and it'll go to negative infinity, and also for positive infinity. Anyway, here's the function plotted for c equal to 0. And there's no c you can choose where you can make this go to 0 for x equal to infinity. So anyway, so there's a typo, but this is the potential energy function. Okay. So there's the graph. Okay. Okay, so we'll do this one. So boy throws a ball straight up with a speed of 20 meters per second. And how much work is air resistance do on the ball during its flight? Okay, so the ball goes straight up and then comes down. Okay, there's a drag force acting in the opposite direction of the motion of the ball. Yeah. And the drag force is a non-conservative force. And drag forces always do negative work. And you've seen, if you look at your notes, the work done by non-conservative forces is change in mechanical energy. So mechanical energy is kinetic energy plus potential energy. And in this case, potential energy is gravitational potential energy. So, okay. So non-conservative force, the drag force, the total work done by the drag force on this trajectory is final mechanical energy minus initial mechanical energy. Okay, now the only potential energy is gravitational potential energy. And at this point, the gravitational potential energy is the same as this. Okay, so these two cancel. Gravitational potential energy is mgy and any reference level. So the y distance is the same. So these two guys cancel. And the non-conservative force is doing this much work. Okay. You see, the ball has slowed down, so final kinetic energy is less than the initial kinetic energy, and so the work done is negative. So the work done by the drag force, which is the non-conservative force, is 1/2 mv final square minus 1/2 mv initial square. There's V final, there's V initial, and there's the mass. All right, so you guys can calculate that. All right, so here's a problem where this problem is interesting because there are two conservative forces acting. What are the two conservative forces that you know about? Spring and gravity. And so in this problem, a spring force is acting and the ball is moving up and down, so gravitational force also has an effect on this problem. So this problem contains both the conservative forces you've learned about. Okay. And when only conservative forces act, what have you learned? You've learned that mechanical energy is conserved. All right, so here's a point that you should be aware of. What is this? Mechanical energy at the initial point, And what is this? Mechanical energy at the final point. What is the initial point and what is the final point? I'm sorry? No. Okay, so you fire the gun and the ball goes there and comes back. Okay, so this is the highest position. What is the initial position and what is the final position in this trajectory, in this motion? It can be any point. Okay, that's the statement. Mechanical energy is constant at all points. Okay, so that's important. You can choose any point to be initial point and any point to be final point. Okay. All right. Of course, we'll choose the most convenient points for us. Okay. So the massless spring of a spring gun has a force constant of 12 newtons per centimeters. Okay. What we'll do is 12 newtons per centimeter. We want to convert that to SI unit. We want to convert that to meters. Okay. So 12 newton and a centimeter is 10 to minus 2 meters. So this is 1200 newton per meter. Okay, so this is the spring constant. On what this means is 1200 newtons is roughly twice our weight. So two of us would have to hang on to the spring to stretch it by 1 meter. That's what that number means. Okay? And that's the kind of spring you have in those toy guns. All right, so they tell you that. So when the gun is aimed vertically, a 15-gram projectile is shot to a height of 5 meters. 5 meters is roughly the height of the ceiling. Okay, so you shoot the gun and it will go that high. How much was the spring compressed initially? Okay, so so there's the uncompressed position of the spring. You compress the spring, you shoot the gun, and the ball rose that high. Okay, so this will be our initial position. Okay, and this will be our final position. Again, you can choose any two initial and final positions, but we are choosing this because depending on what it is that we want to solve for. Okay. All right. So I'm going to write what is mechanical energy, kinetic energy initial, plus initial potential energy, and what are the two conservative forces acting in our problem? Yeah. So we have to account for those mgy initial, and that's equal to kinetic energy final plus potential energy in the final configuration of the system. Okay. All right. So here's our initial position, and here's our final position. Okay. And what we'll do is, see, mgy. Okay, so this is gravitational potential energy. And this y is with reference to some level. Okay, so what we'll do is we'll choose this as the reference for the vertical position. So that's where we'll draw our origin. So y initial will be 0. Okay. What was initial kinetic energy? 0. Okay. So this guy is 0. You fired the gun from, the bullet was at rest. What is the kinetic energy at this point? 0. It's come to rest at the highest point. Okay. This was 0 because that we chose that to be. Okay. What was this fellow? The initial compression of the spring is D, and that's what we're trying to solve for. Okay, so this is 1/2 k d square equal to 1/2. All right. Okay, what is this? In the final configuration, how much was the spring compressed? None. Okay, so there the ball and the spring has come back to its original shape. So there's no spring potential energy in the final configuration. Okay. All right, and so that's equal to mg y final. What is y final? This is 0. So y final is 5 meters plus d. So that's equal to mg 5 plus d. Okay. So what have we solved for? See, what this is showing you is, see, this is the spring potential energy that got converted to gravitational potential energy. So that's what happened in this problem. Okay. In this conservation of mechanical energy, spring potential energy got converted to that. Okay. Now let's look at it mathematically. What is it that we're trying to solve for? D. Okay. You guys understand that the more you compress the spring, the higher the ball would go. Okay. So what we are doing is we're calculating from how high the ball went, we're calculating how much the spring was compressed. All right, now let's look at it from a mathematical perspective. See, here's a d square, here's a linear d term, so this is a quadratic in d, and you solve for it. Okay? All right. K was 1200 Newton per meter. That divided by 2, that's 600 d square. Okay. Mg, the mass is 15 grams, so 15 into 10 minus 3 kgs. And again, I'm not writing units because I don't want this thing to get messy. But so 600 d square. All right. Okay, so there's a quadratic equation and you can solve for that. Okay? I'll let you guys do that. So you will get two solutions. Okay. All right, actually I'll do that. So d is minus b plus or minus b squared minus 4ac divided by 2a. There is b, so plus 0.147 plus or minus a is 600. Okay, so 3.5 centimeters, which is 1.5 inches, which is roughly about how much some of you did the lab in the projectile motion. That's how much you compress the spring. Except that spring was much weaker. Why was that spring much weaker?
Shoot 5 meters in the air.
Well, yeah, we are worried about you taking out your eyes. Okay. So that's what we're worried about. Yeah. All right.
How do you manage to get D into the equation? So originally you didn't have any D. You managed to get it somehow. Not quite following how you got that in there.
That was the initial spring potential energy. That's how much the spring was compressed. X initial is equal to D. Okay, so here's another interesting solution. So this is why I solved this. Okay, so what is your D? It's this guy. What is this other guy? It's negative. And you see this solution is smaller than that guy. What's that? Well, you're almost right. So what that is the following. If the bullet was stuck to this thing would go up that high. The ball would go up that high. Okay, why is this smaller than that? I'm sorry? Yeah, so this was all spring potential energy. When it's that high, it has spring potential energy plus gravitational potential energy. So that's why it's not going that high. Okay. So that's what happens. So let's say if you're attached to a bungee and jump off a bridge, from the equilibrium position, if you go down 10 meters, when you come up, you won't go up 10 meters as high. All right. Okay, I'll do two more problems. All right, so two more problems. Okay, this says a single force Fx equal to that. So you see this is a spring force. There's the spring constant. Okay. Acts on a 1 kg body when x equal to 3.5 meters and the speed of the body is 4 meters per second. What is its speed when x equal to 2 meters? Okay. So you have the work energy theorem, which says the net work done is equal to change in kinetic energy. So in our problem, you have a single force. So if you calculate the work done by that force, that's the net work done, because that's the only force acting on the object. Okay. And they give you the speed of the body at the initial point, and they give you the speed at the final point. Okay, so they have given you these terms. And so you can calculate whatever it is that they're asking you. Okay, so work done is equal to, from the initial point to the final point, Fx dx should equal 1/2 mv final square minus 1/2 mv initial square. All right, this is minus 4x dx. And so the initial position was 3.5 meters. What is the speed at 2 meters? Okay. And this is minus 4x squared by 2, 3.5 to 2. By the way, you guys remember, so let me draw the spring. So this is x equal to 0. The initial position is 3.5 meters. So let's say this is 3.5 meters. And the final position is 2 meters. So as the mass is coming over here, what is happening to the mass? Is it speeding up or slowing down? It's the spring is pulling on the mass, so it's speeding up. Okay, so V final should be greater than that. Okay. All right, so this is equal to minus 2 times 2 square minus 3.5 square, which will be a positive quantity. Okay, so the work done by this force was 16.5 joules. That's what we've calculated. And that should show up as the change in the kinetic energy. Okay, so 1/2 m V final square minus V initial square. And the mass is 1 kg, so 1/2 times 1. V final is what we're trying to solve for. V initial is 4 squared. Okay. So 16.5 is 0.5 times V final square minus 16. Okay, so as promised, the final velocity is greater than the initial velocity. Okay. Okay, so again, the mass is attached to the spring. Okay, the initial position was 3.5 meters, and it was, let's say, moving at that speed in that 4 meters per second. And then the final position was 2 meters, and so it's moving faster. Okay. All right, we'll do one more problem. Okay, this problem says a 60 kg skier, 60 kg is most of our masses, okay, with an initial speed of 12 meters per second coasts up a 2.5 meter high rise. Okay, so 2.5 meters. 2.5 meters is roughly, so up to the height of that, halfway to the height of that periodic table. Okay, so you're climbing a hill that high. Find her final speed at the top, given that the coefficient of friction between her skis and snow is 0.8. Okay, so there's the skier, and we want to find the speed of the skier there. There's friction acting, so when the skier is here, okay, so we're going to start the skier right at the bottom, and the friction is acting there. What kind of friction force is it? Kinetic friction force, okay? And friction force is a non-conservative force, so what it does is it bleeds energy, it removes mechanical energy, okay? So work done by non-conservative force, the friction force, is equal to final kinetic energy plus final potential energy minus initial kinetic energy. Okay, non-conservative forces changes mechanical energy. Here's mechanical energy final, here's mechanical energy initial. Okay, what kind of work is being done? Positive or negative? Negative work is being done. So final mechanical energy will be less than initial mechanical energy. Okay, what kind of potential energy is involved here? Gravitational potential energy, the only conservative forces act. So we'll take this as the reference level. mgy is gravitational potential energy. We'll take this y to be 0. So final, okay. So initial potential energy will be 0. We know the initial speed of the skier is 12 meters per second, and final speed, so we know this, final speed is what we're trying to find. We also know the final potential energy. Okay. All right, so now let me just draw the slope. Okay, so the slope here is the following. Okay. So here's the skier, mg, and remember this is mg cosine theta. Okay. This is mg sine theta. Okay, so that's the component of gravity that's slowing it down, but the work done by this guy is taken care of in the potential energy. Okay, here all we have to do is take care of the work done by the friction force. Okay, so the friction force is in this direction. All right, and the normal force is equal to that. Okay, so the friction force is equal to mu k times the normal force, which is mu k times mg cosine theta. Okay. And so 0.8 times cosine 35 mg. I'll write things in terms of mg because you'll see the masses will cancel. Okay, so the friction force is 2/3 the weight of the person. Okay, that's what that means. All right, how much work is the friction force do? We have to calculate this distance. Okay, you know this distance, 2.5 meters, and you know that angle. So let's calculate that. So this is 2.5 meters. D, this is 35 degrees. Okay, so you can see that sine 35 is 2.5 divided by D. So D is 2.5 divided by sine 35. So 4.36 meters is the length of the slope. Okay, so the work done by the friction force is minus FD, and that's equal to 0.66 mg times 4.36 meters. Okay. And that's equal to change in kinetic energy. So the non-conservative force, oh, that's equal to this guy. Okay, so work done by the friction force equal to kinetic energy final plus potential energy final minus initial kinetic energy. Okay. So minus 2.88 mg equal to 1/2 mv final square plus mgy final minus 1/2 mv initial square. And notice here something interesting. What does that mean? I'm sorry? That's right. So every skier would be going at the same speed there. Okay? So if you were going in the opposite direction, you'd be going as fast. So the slope is equally fun for everybody. Okay? So, all right. So now you can put in the information and calculate the speed. So minus 2.88 times 9.8 equal to 1/2 v final square plus 9.8 times, again, I'm not writing units just because I don't want it getting messy. You guys should be writing units. 12 square. Okay. And you can solve for v final. So this is v final square is 12 square minus 2.88 into 19.6 minus 2.5 into 19.6. So V final works out to 6.2 meters per second.